Oh, loud. Okay, Lauren, help us out. How do I find the moment of inertia?
I set up I equals I plus nx squared.
Okay, now you're using the parallel axis theorem. I don't know that we need to use the parallel axis theorem unless you're using it in a way that I'm not expecting. What did you use for ICM? What?
I use the moment of inertia of the rod.
Okay, about its end or its middle?
Its middle.
Okay, so you are going to move it from its middle to its end?
Oh, I don't know actually. I just use 1/3 ml squared. So.
Okay, so 1/3 ml squared is the moment of inertia of the rod about this point. So that's good. That's what I would use, 1/3 ml squared. But we don't need to use the parallel axis theorem, but we do have to add the moment of inertia of this point mass, which is located at the bottom of the rod. And I don't want you guys to be confused about this, but I want you to understand that it's going to look like it's the parallel axis theorem, but it's not. It's just that we have a point mass at the bottom that's being added onto it. So it's two different masses. This is the mass of the rod, and then we're adding the point mass at the bottom. So this is the mass of the point mass. So I know it has a look like it's the parallel axis theorem, but it really isn't. So 1/3 times 5 times 1 squared plus 2 times 1 squared. And that's it. I left it as a fraction. Did you guys leave it as a fraction? I think it's 11 thirds. Yep. And the units are kilograms meter squared. That is the moment of inertia. All right. Again, you can't figure out the mass from this. The mass is 7. So, I want to kind of remind you. And it was funny because funny is the wrong word here. One of the students, I'll leave them, anonymous again. But Max asked, well, don't we have to figure out the moment of inertia about the center of mass? No, it never spins about its center of mass. We do need the center of mass, but it's never going to spin about its center of mass. And I do want to throw this at you because he went on and asked me some other questions about it. And that's where I realized I kind of misinterpreted what he was asking. The moment of inertia never has to be determined first from its center of mass. You can pick your point and determine an object's moment of inertia from any point you want. The parallel axis theorem works from the center of mass. That's the only thing that requires, that we start with the center of mass. And even then, we don't have to. We could solve for the moment of inertia about another more convenient point, perhaps, and shift it to the center of mass in a situation where it might be easier to distribute the mass somehow different. I don't have an answer to why, but the parallel axis theorem is something separate from this completely. All right, so we have question number 2, which is finding the angular speed after the collision. Karen, can you tell me how to do that?
Yes, you do RMV equals I omega.
All right, so what is, and I'm not trying to put you on the spot here. You said use RMV. What does RMV represent?
The momentum times the, I forget what it's called, the closest approach.
Okay, so we're talking about the angular momentum of the box. We're setting that equal to the angular momentum of the system. I'm not trying to correct you. You said everything perfectly. What I'm trying to do is establish that this is a conservation of momentum question, but it's not the linear momentum because the linear momentum isn't conserved. And I had a long discussion with 4th period about being able to describe why one of these is conserved and why the other one isn't. And we had already talked about this yesterday, folks, but an interesting question was brought up in 4th period, and I want to kind of reiterate it here. Before the collision takes place at all, there is an upward force that's being applied to the bar from the pivot point. It's holding the bar upright, right? That's what it's there for, you know, to keep it from falling or whatever. When the box hits it, there's probably an additional force from the pivot to the left. This keeps the bar from moving to the right, keeps it in place. Now it might swing upwards, but as an object goes, it is fixed in place and is probably experiencing, you know, two components of the force now acting at the pivot point. This is why linear momentum isn't conserved, because by Newton's third law, that would mean when the box makes it here, it experiences a force to the left as well. That's what changes the linear momentum of the system. Now, all that being said, the angular momentum is unaffected because both of these forces act at the pivot point and therefore cause no torque. I'm not trying to say this for my health. I'm saying this because when I give you a problem, say in the next 15 minutes, you'll need to figure out just by looking at it what's conserved and what isn't. You need to have a sense about it. If there was no pivot point, this is not rooted to the wall, linear momentum would be conserved. The system would probably be moving to the right after this, but the linear momentum would be conserved. It's because it's rooted in place that the linear momentum is not conserved. All right. So you already said this, but I'm going to go ahead and say it again. You said R perpendicular times MV equals I omega. We have everything here. This is 2 times 1 times 2. Sorry, 1 times 2 times 2. R perpendicular is 1 meter. Mass is 2. Velocity is 2. And I is 11/3 omega. So omega is going to be 12/11. This is radians per second. All right. Ryan, can you tell me how to find the center of mass? Yeah.
Yeah, I started from the pivot point.
Ryan Scott, I actually was asking to Ryan in class. I'm sorry.
Ouch.
I got you for energy though, okay, Ryan? All right. Sorry, I will make sure that I turned the stereo. I adjusted the volume. I will fix it. Go ahead, Ryan, you're up.
All right, so I set the pivot as my reference point, and then did the 5 kilograms of the bar times half a meter.
Okay, so let me just repeat this for the folks at home. Ryan set the pivot point to be the reference point. So then he said that, I didn't hear the next part.
The 5 kilograms of the bar times half a meter.
Okay, so mass of the bar times half a meter. That's the contribution for the bar and
then 2 kilograms of the box times 1 meter.
contribution center mass from the box. Now it's attached to it. What do I do next?
And then divided by 7 for the total mass.
Perfect. So 4.5 over 7. There's probably a decimal here I should probably use.
0.64.
Unit here is just meters. That's all you need there. Excellent. Thank you.
Mr. Sean,
Yes.
so say we picked like the bottom as the point, we should just say 0.36 from the bottom.
Sure. There's a specific reason why I would pick the pivot point over the bottom. And that's because when we start doing this problem as a conservation of energy problem, we're going to be looking at how high the center of mass was lifted from the ground. And that's like treating this as if this is just a pendulum where its lowest point, you know, was here. But we can't do it that way because we suddenly added weight to the bottom. So we have a certain amount of kinetic energy just as the system begins to move. But we need to figure out how high the center of mass was lifted. Now, I think we're about to see a mistake here. So I'm curious to see how we go from here. So, well, maybe we won't see a mistake. Ryan might have got it nailed. So go ahead, Ryan. No, this is Ryan Scott. This one's him. He gets this one. Sorry, 2 Ryans, 2 Laurens, same class.
Okay, so I started with setting mgh equal to 1/2 iw squared. I mean I rotational velocity squared.
Excellent.
And then I substituted m with 7 and g and h, which is equal to 1/2 11/3 times 12/11 squared.
Okay.
And then I solved for h, which got me 2.917.
I have to believe you. I
Okay.
didn't do it this way. That seems really high
Oh, wait, yeah.
because that's like 3 meters, and that means we've like
Yeah.
looped around a couple times. So maybe there's a mistake there in the arithmetic.
Probably.
But let's see if we can't nail this. And there's nothing wrong with the way we're doing it right now. So let's go ahead and continue. But let's get the correct number for h. So for those of us who all have calculators, which is not me, can you guys fire away there? You know,
Oh, wait, oops.
I'm gonna see 144 divided by 6. No. 144 divided by 66. Then divided by 70. I can't do all that in my head. What? 0.03116. Anybody else get that?
I got that.
All right, so that isn't our answer, but at least that's a start. This is how high the center of mass of the system has to be lifted. How do we get the angle from that?
L1 minus cosine.
I was actually asking Ryan, but
Okay.
You could use trig functions.
yes, there's a specific thing we should do. What should we do?
Uh,
I'll give you a hint. It rhymes with L1 minus cosine theta.
is it L1 minus cosine theta?
That's exactly what you should
H?
do. But what do we do for the L here? Because L in the past has been this entire length. In this case, it's not going to be that entire length. We are lifting the center of mass. So instead of L here, we might want to start thinking about putting X center of mass here. Because that's what this really has to be. We are lifting the center of mass, and the center of mass now is effectively what L is going to be. So finding the angle now, we're going to have, I'm just going to do it over on this side, 0.03116 equals X center of mass, which is 11/3 times, it is not 11/3, thank you, 0.64 times 1 minus cosine theta. Got to get an angle. That's the end. So I'm sure somebody has this angle. Brett?
Well, do you not take into account the linear kinetic energy that it also has, or the translational kinetic energy that the block has when it hits afterwards?
No. But I will tell you why after I get this angle.
Okay.
So let's just get the angle real quick so we finish out the question, and then I will answer your question, Brett. Dylan?
It's 17.9.
17.9?
I can agree.
Of course, you know I'm going to put 18, right? Not terrible. Level of difficulty, probably a little bit high right now, a lot of parts, but do you understand once you've done this, it's got to be the same way every time? Object hits some physical pendulum. Question 5, what's the period of oscillation or some garbage like that, you know? That's where we go next. But let's talk a little bit about the question that Brett asked, and I want you guys to see this. So you guys are pretty sharp people. I want to follow up with this for just a minute, if you don't mind. Let's just have another page for just a minute. The box directly after it comes in contact with the rod, the box and the rod are both moving. and they both have kinetic energy. Now, we treated this like one system. But the truth of the matter is, this system has an angular speed equal to, I can't remember what. Thank you, 12 over 11 radians per second. The moment of inertia of the system was 1/3 ml squared plus ml squared. Big M for the rod, little m for the box. The kinetic energy of the system, as we used it in the problem, was 1/2 I omega squared. You good right now? Everybody follow? That's what we did in the problem. What I'm explaining to Brett is why we don't have to add the kinetic energy of the box by itself. And I want all of you to pay attention because that's actually an excellent question. We are treating this as a single unified object, but we actually didn't have to because our object actually was broken up into two things. Correct? So I could have said that this was the kinetic energy of the rod plus the kinetic energy of the box. Right? I can separate it like that. They are two separate objects. They could have their kinetic energies separated because you just add kinetic energies together for a system. But the box is attached at the bottom of the rod, which means that its linear velocity could be computed as omega times L, which means I could substitute V over L here. If I distribute, I get you guys see it okay? So this is the rotational kinetic energy of the rod on its own, separate from the translational kinetic energy of the box. The fact that they are linked together is important, but the linear kinetic energy is still in there. By treating it as one system, though, we already had the moment of inertia of the system, and therefore each of the pieces of the system, since they all had the same angular velocity, could be treated as a single object with one kinetic energy. But you can break it up. You can have multiple objects here. It's fine. Good stuff? Good stuff. We have what, like 10 minutes? Not even 10. All right. So if you will look at Canvas, I'm going to bring something up for you guys to take a look at. So it's on Canvas. You don't have to hurry to there. I'm going to put it up in front of you anyways, so that you'll have to see it. This is on Canvas right now. And it is an FRQ I would like you guys to kind of run through tonight. My goal had been for us to work this out in the classroom, and we don't have a whole lot of time to do so. 6 minutes gives us about 1/3 of the amount of time necessary. But I wanted you to see the kind of way in which these problems are asked on the AP exam. This is an oldie, but not terribly old, not like the ones you saw before. This one, though, is in the 80s, so it's still pretty old. We are looking, if you look, it says top view. So we're looking top down on this. Gravity is not acting on this system to cause this pendulum to oscillate. This is like a baseball bat striking a ball on a horizontal surface. Does that make sense? There's a clear pivot point. So this object is attached to the table and is pivoted about point P and strikes object 2 in this collision. This is right in line with what I think a modern day problem like this would look like. Even though it's pretty old, modern problems have this look to them. So I'm going to stop talking now. I would like you to finish this problem by tomorrow, but I want you to time yourself 15 minutes. I've given you some mastering homework, so I'm not trying to add to your homework. I really want to do this in class. So the last 5 minutes are for you guys to work on this, read through it. If there's something that's being asked you don't understand, get it clarified before you go home. I will not ask you to come to class with it complete. I will give a few minutes at the beginning of class tomorrow for you to complete the problem, because you have homework already and it's pretty long. Next week, Thursday, I think. I think I intentionally did not make it due the same day as E&M. You're welcome. I'm also probably going to be absent Wednesday. I have to go someplace with my mom and my daughter and my wife, and we may all be going someplace. We might be taking a vacation day. I've earned it. I slid it down so you guys could read the bottom of it. There's another problem that's hidden. So quiet in here. You guys will all be talking.